Good morning, class. I am Professor Joe Rogan, but I am entirely generated by machine learning. Today, we will be discussing deadlock and why it can be a major issue. Deadlock is a state where a system is unable to progress further due to the fact that each operation has acquired a shared resource that the other operation needs. To illustrate this concept, think of a four-way intersection where two cars are stuck and unable to pass each other. In this situation, no car can make progress unless one of them backs up to allow the other to pass. The same idea applies to deadlock. In a deadlock situation, there is no way for any thread to make progress unless one of them relinquishes the resource that the other needs. Deadlock can be a major issue because it can cause a system to crash or become unresponsive and can be difficult to debug and resolve. Deadlock can also occur in computer systems. For example, thread A might produce work for thread B's work queue, and thread B might produce work for thread A's work queue. However, if the queues are finite and the workers wait, if no output space is available, deadlock can occur. Another example is when a thread sends a message to the thread with the next higher ID and then receives a message from the thread with the next lower ID. In this case, a deadlock can occur if the threads are both sending and receiving messages at the same time. Deadlock can be a huge issue in computer systems. So it is important to be aware of the potential for deadlock and to design systems to avoid it. As discussed, deadlock can be a major issue in computer systems. In order for deadlock to occur, four conditions must be met. First, there must be mutual exclusion, meaning only one processor can hold a given resource at once. Second, the processor must hold the resource while waiting for other resources it needs to complete an operation, which is known as hold and wait. Third, there must be no preemption, which means processors don't give up resources until the operation they wish to perform is complete. Finally, there must be circular wait, which means that waiting processors have mutual dependencies and a cycle exists in the resource dependency graph. With these four conditions in place, deadlock can occur.